Now let's look at a few more examples before we turn to the question of convergence and whether the Taylor series converges to the function. Starting with the problem of finding the Taylor series for the polynomial function 1 plus x squared at a equal 2. Well, if we go just by the definition, the first coefficient, C0, is going to be the value of the function at 2. If we plug x equal 2 in the function, we get 1 plus 2 plus 4, 7. On the other end, to get the second coefficient, we get the first derivative of the function evaluated at 2. The first derivative here is 1 plus 2x. When I plug x equal 2, I get 5. The next coefficient is the second derivative of the function at 2 divided by 2. If I look at the second derivative, it is a derivative of 1 plus 2x, so it is a constant function 2. So I get 2 over 2 is 1. But then, if I look at the third derivative, I'm differentiating the constant function 2, so I get 0. And so the third coefficient is 0. And so are all the coefficients after for n greater or equal to 3, because then the derivative is of order greater or equal to 3. And if the third derivative is the function 0, then so is the fourth derivative, the fifth derivative, and so on. So all the coefficients for n greater or equal to 3 are 0, and that means that our Taylor series is just composed of 3 terms, 7 plus 5 times x minus 2 plus 1 times x minus 2 squared, because we're looking at the Taylor series centered at 2. Now in this case, of course, we can easily see that we have equality. You just multiply things through and you see that what we get is 1 plus x squared. And of course here, using the Taylor series is really very big hammer to crack a small nut, because all we did is rewrite this polynomial of degree 2 as powers of x minus 2 instead of powers of x. So we could have done that by simple algebra. It's just translating the variable by 2. And of course, in that case, we have automatic convergence, and the function is equal to the Taylor series. And the Taylor series in this case is not really an infinite series, but just a polynomial of degree 2. Turning to the second function, we are looking for the Taylor series of 1 over x at a equal 1. So again, the nth coefficient in our Taylor series is the nth derivative of the function evaluated at a divided by n factorial. So we need to find a formula for the nth derivative of f. Of course, the derivative of order 0 is just a function, that's 1 over x. I'm going to write it as x to the negative 1. And then when I differentiate, get the derivative of order 1 is negative x to the negative 2. When I differentiate again, I get the derivative of order 2. And I'm going to write, to keep this negative sign as negative 1, I multiply that by negative 2 and then by x to the negative 3. And I'm not going to simplify this negative 1 times negative 2, simply to see better what happens when we keep differentiating. For the derivative of order 3, well, I have this constant negative 1, negative 2, and then the derivative of x to the negative 3, which is negative 3x to the negative 4. So I end up with this product, negative 1, negative 2, negative 3 times x to the negative 4. If I was differentiating again, you see that I would have the constant in front and then the derivative of x to the negative 4, which is negative 4x to the negative 5. So if we keep going that way, when I differentiate n times, I have negative 1, negative 2 all the way to negative n. Just like for the third derivative, we went all the way to negative 3. And then x to the negative n plus 1. You see that for derivative of order 2, we add x to the negative 3, derivative of order 3, x to the negative 4. So one way to rewrite this is to look at this product of n numbers, negative 1, negative 2, negative n, pull out the negative sign each time, so we have n numbers, each one of them is negative. We can write that as negative 1 to the n multiplied by 1, 2, 3, 4 up to n. But this product of 1 through n is just n factorial. And you see that this formula matches what we have with our convention, because now the derivative of order 0, that corresponds to n equals 0. If I plug that in my formula at the bottom, I get negative 1 to the 0, that's 1. 0 factorial, that's 1, x to the negative 0 plus 1, so that's x to the negative 1, so that matches. Then when n is 1, I get negative 1 to the 1, that's negative 1. 1 factorial, which is 1, x to the negative 2, so I get negative x to the negative 2, that matches. When n is 2, I get negative 1 squared, that's positive 1. 2 factorial, that's 2 times x to the negative 3, so that matches again. So we didn't really need to check that our formula matches the first few terms, but it's usually a good idea for you when you've obtained a formula, a general formula for the nth derivative, to check that everything matches for the first few terms of your derivatives. So now, to find the nth coefficient in the Taylor series centered at 1, we just plug x equal 1 in the nth derivative and divide by n factorial, and that's the nth coefficient. So we get negative 1 to the n factorial, 1 to the negative n plus 1 divided by n factorial. The n factorial cancels out, a power of 1 is always 1, and so we end up with negative 1 to the n as the nth coefficient. In other words, the Taylor series is simply the series from 0 to infinity of negative 1 to the n, x minus 1 to the n. At this point, from these calculations, what we can conclude is that this is the only possible power series representation of this function centered at 1, but we don't know anything about the convergence or whether it agrees with the function. However, in this case, we can easily check that the function is equal to this Taylor series, at least when the distance between x and 1 is less than 1. Indeed, 1 over x is really 1 over 1 minus 1 minus x. And if you, it is easily verified, and under that form you have something of the form 1 over 1 minus something, and that's really the geometric series of common ratio 1 minus x starting at 1. So this is equal to the sum from 0 to infinity of 1 minus x to the n, as long as the common ratio 1 minus x is in absolute value less than 1. Now this 1 minus x to the n, I can write negative 1 times x minus 1 and raise that to the n, but then that's really just negative 1 to the n times x minus 1 to the n, and that is valid as long as the common ratio is less than 1, but the common ratio 1 minus x, its absolute value is the same as the absolute value of x minus 1 and is simply the distance between x and 1. So for x at a distance less than 1 from 1, the function f of x here is equal to this Taylor series. Now for the third example, we are looking at the function f of x equals sine x at pi over 4. And so again, we're going to look at the successive derivatives. The derivative of order 0 is the function itself, sine x. When I differentiate sine x, I get cosine x. When I differentiate cosine x, I get negative sine x. When I differentiate negative sine x, I get the opposite of the derivative of sine x, so negative cosine x. And when I differentiate that again, I have minus derivative of cosine, which is negative sine, so I get again positive sine, which was the function. So we go back to the original function, which means that when we keep differentiating, the fifth derivative is going to be the same as the derivative of f, in other words, the first derivative. The sixth derivative is going to be the same as the second derivative, and so on. So in particular, you see that we obtain sines for the derivative of order 0, of order 2, of order 4, and then we go back to the order 4 corresponds to order 0, and then we go back again to order 2, order 4, and so on. So, in other words, we get sines for order of differentiation 0, 2, 4, 6, 8, and so on. Therefore, for the even orders of differentiation. Additionally, you see that we have an alternance of signs. So for order 0, we get positive sign, for order 2, negative sign, for order 4, positive sign, for order 6, negative sign, for order 8, positive sign, for order 10, negative sign, and so on. So that means that the derivatives of even order, which we can write at the derivative of order 2n, is really negative 1 to the n sine x. And you see that it matches what we have, because when n is 0, or so when n is 0, we are looking at the derivative of order 0, we get positive sign. When n is 1, we are looking at the derivative of order 2, we get negative sign. When n is 2, we are looking at the derivative of order 4, we get positive sign, and so on. Similarly, you see that we get cosines for the derivative of order 1, of order 3, and then of order 5, which is the same as the derivative of order 1. Then for the derivative of order 7, which is the same as the derivative of order 3, and so on. And so we get cosine each time we look at a derivative of odd order. In other words, we are looking at derivatives of order 2n plus 1. And each time we're going to get a cosine. And additionally, you see that it is exactly negative 1 to the n cosine x, because for n equals 0, you get negative 1 to the 0 is positive 1 times cosine. That's the derivative of order 1. When n is 1, you get the derivative of order 3, and you get negative cosine. When n is 2, you get the derivative of order 5, which is positive cosine, and so on. So in this case, we really don't need this distinction that much, but these formulas for the derivative of odd order and even order are going to be useful for us when we look in a moment at the Maclaurin series for sine x. In this case, we're looking at what happens at pi over 4. At pi over 4, both sine and cosine take the value root 2 over 2. And so all we can say is that for this, when we plug x equal pi over 4 in these various derivatives, we get alternatively positive root 2 over 2 and negative root 2 over 2, but we get 2 positive terms and 2 negative terms and 2 positive terms and 2 negative terms. So we get here power series, that is a Taylor series that is going to look like that. Each term is multiplied by root 2 over 2. Then we have 2 positive terms, so let's say 1, and then 1 times x minus pi over 4. Then we have 2 negative terms, negative 1 twice, and then of course it's multiplied by the expression you have in your Taylor series, which is x minus the center, x minus pi over 4, to the exponent that we're looking at, divided by the same exponent factorial. So in this case, we get 1 plus x minus pi over 4 minus x minus pi over 4 squared over 2 factorial minus x minus pi over 4 cubed over 3 factorial plus x minus pi over 4 to the 4 over 4 factorial plus x minus pi over 4 to the 5th over 5 factorial, and then again 2 negative terms, and then again 2 positive terms, and so on. And each one of these terms is multiplied by root 2 over 2. And that's our Taylor series. We're not going to worry too much about writing a formula with a sigma sign for this Taylor series. I'm just going to look at what happens for the Maclaurin series, so at a equals 0. Since we have these successive derivatives of even order and odd order given by these formulas, all we need is to plug x equals 0 in this, and you see that if you plug x equals 0 in the derivatives of even order, you get 0 because sine 0 is 0. For those of odd order, you get negative 1 to the n because cosine of 0 is 1. That means that in the Maclaurin series, all of the terms corresponding to a even power of x have coefficient 0, and therefore they disappear in the series. And all the coefficients corresponding to odd power of x have coefficient negative 1 to the n, where the power of x is of the form 2n plus 1. In other words, the Maclaurin series is the sum from 0 to infinity of negative 1 to the n multiplied by x to the 2n plus 1 divided by 2n plus 1 factorial, if we are to follow the formula for Maclaurin series. So that means when n is 0, you get positive 1 over 1 and then just x to the 1. So in other words, the first term is x, and the second term is going to be minus x cubed over 6, and then plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. Now it's easy to see, you can use a ratio test, for instance, to check that the interval of convergence for this power series is the entire real line. And of course it is natural to ask, well, since you have an interval of convergence that is the entire real line, this power series converges to a certain function, and the only power series representation centered at 0 possible for sine x is exactly this. So is that function given by the sum exactly sine x? It is the case, and we're going to discuss that in the next video. So now turn to the next video to see what we have to say about that.